So this is the thought for today. God helps only people who work hard, and that principle is very clear. So hi everyone, welcome to another session on design emission elements. Today we will see how to design a pressure vessel. Pressure vessels are those which are used to store fluids under pressure above atmospheric pressure. The normal gas cylinder which we see in our home and the tankers which carry LPG gas which we see in our roads are all pressure vessels. Our boiler is a pressure vessel. So how to design such pressure vessels? The pressure vessels are subjected to very high pressure, internal pressure, due to which it can fail either along a longitudinal direction as seen in figure A, or it can fail along a cylindrical shape along the transverse direction. Suppose if we consider the first failure, I can find the equation for this one. The total pressure will be acting on the internal surface. So this is a figure. So pressure multiplied by the projected area LD is resisted by this shaded area. That shaded area will be 2T into L, where L denotes the length and T denotes the thickness. There is thickness on two sides, so 2T into L. There is the area multiplied by the stress. Since the stress is acting along the circumference, it is denoted by sigma c, circumferential stress. So circumferential stress sigma c equal to PD by 2T. When we consider the failure along the transverse direction as in figure B, that pressure is acting on the N side. So this is our pressure vessel. If we take the front view, the pressure is acting here. So on the side view it is a circle of dia D. So pressure into area, pressure P into area of this circle will be pi by 4. D square is resisted by this area. And what will be the area of that shaded one? That area will be pi d into thickness. Thickness is this length, so pi d into T into that stress is acting along longitudinal direction. So I am denoted by sigma L into sigma L. So I will get sigma L equal to PD by 40. So from these two equations, sigma L equal to PD by 40 and sigma C equal to PD by 2T, I can write sigma C is greater than sigma L. So what happens is that circumferential stress is greater than longitudinal stress. So it has more chance to fail along the circumference, or failure of cylindrical cell is more prominent along longitudinal section. This is the most prominent mode of failure. Okay. Now we'll see what is a thin cylinder. We have already seen the thickness, the diameter to thickness, that ratio, thickness T and the internal dia D. If T by D less than 0.07, it is called a thin cylinder, usually used for low pressures. At high pressures we use a thick cylinder. So we have different equations for thin cylinder and thick cylinders. First we will see design of thin cylinders. These are very simple questions. Design a thin cylindrical pressure vessel 1.2 meter inner dia producing steam at 1.75 Newton per mm square. So we have the pressure. Find the minimum wall thickness if the longitudinal stress sigma L equal to 28 megapascal and circumferential stress not to exceed 42 megapascal. So this is our question, very simple one. So we have to find the thickness T using the equation from page 99, equation 7.1b. Sigma T is known, that is the tensile stress acting along the circumference denoted by circumferential stress, which is given as 42. Inner dia is given 1200 mm, 1.2 meter equal to 1200 mm, and internal pressure equal to 1.75 Newton per mm square. I can get the thickness, very simple. Thickness equal to 25 mm. 25. Further, I can design the pressure vessel according to longitudinal stress also. So as per longitudinal stress, the maximum longitudinal stress allowable was only 28. Inner dia remains the same, 1200 mm, and pressure equal to 1.75. I can get thickness equal to 18.75 mm. And if you have got two values for thickness, you should select the higher value. Further, we have to find the maximum shear stress. Here, I can say the circumferential stress and longitudinal stress act along perpendicular direction. So if I take a section on that pressure vessel, sigma L will be acting along x-axis and sigma C will be acting along y-axis. So maximum shear stress equal to sigma x minus sigma y by 2. Here sigma C is higher, so I can write sigma C minus sigma L by 2. That will be the maximum shear stress. So maximum shear stress equal to 42 minus 28 divided by 2. CS denoted by circumferential stress sigma C and LS denotes the longitudinal stress sigma L. So this is our equation for maximum shear stress. So this completes our first question. Very simple questions. Now we will go to the next question. A pressure vessel consists of a cylinder 1 meter inside dia, closed by hemispherical lens. Pressure intensity P equal to 2 Newton per mm square. Material is steel whose ultimate strength tension is 420 megapascal. Calculate required wall thickness T and thickness of the ends considering factor of safety equal to 6. Whenever we have given factor of safety, we have to divide the given stress by factor of safety to get the design stress. Neglect localized effects at this junction and work. Okay. So tensile stress equal to tensile stress or design stress. I can write it as design stress, which we use for the calculation, equal to ultimate stress sigma u by factor of safety. Given ultimate strength equal to 420 megapascal and factor of safety equal to 6, I will get design stress equal to 420 by 6 equal to 70 Newton per mm square. Now we have to find the wall thickness. Wall thickness, we have the equation sigma C equal to PD by 2T. So from this equation, pressure is known. Pressure equal to 2 Newton per mm square. Newton per mm square. The maximum stress we can allow is up to 70 Newton per mm square. Inner dia is 1000 mm, 1 meter. So I will get thickness T equal to 14.3 mm. So we have found the wall thickness. Now thickness of the hemispherical ends, sigma T equal to PD by 40. Here also same values are known. So you will get thickness equal to 7.15 mm. These are very simple equations for design of thin cylinders. Now we can go to the next question. This is a question on thick cylinder. So for thick cylinder, we have a higher thickness, and that ratio will be T by D will be greater than 0.07. Consider this question. Question number 1. Internal dia is 200 mm. Thickness is 50 mm. So my T by D will be equal to 50 by 200 equal to 0.25, which is greater than 0.07. I have to use, in such case, I have to use the equation for thick cylinder. And thick cylinder equations are normally done by Lamy's equation, and we have other equation of Clavinier's equation and Bernoulli's equation. Now, in this question, we have to calculate tangential and radial stress, at inner, middle and outer surfaces. So this is our question. Then, in order to find these stresses, we have the equation in page 103, equation 7.11 A and B. I have the equation for tangential stress and radial stress. So we have to find these values at inner, middle and outer surface. So outer dia is known, inner dia is known. Substituting different values of radius, I can get the value of sigma T and sigma R. We will see how it will look. So this is our section of the thick cylinder. In this question, inner radius is given, inner dia equal to 200 mm. So inner radius Ri, inner radius equal to Ri equal to 100 mm. Then given thickness equal to 50 mm, that is when this one, thickness equal to 50 mm. So outer radius will be equal to 100 plus 50 equal to 150 mm. That gives the outer radius, and mean radius Rm will be equal to average of this 100 and 150 equal to 125 mm. So we have got all these values. Now we have to just substitute these values in our equation. So our outer dia will be, I will rewrite these values. Outer dia will be equal to 300 mm. Inner dia equal to 200 mm. Our equation for tangential stress, sigma T equal to Pi internal pressure, Di square, Di is in the inner dia, divided by 4R square into 4R square plus Do square divided by Do square minus Di square. Here we have already known the value of Do and Di. Do equal to 300 mm, Di equal to 200 mm, internal pressure equal to 5 Newton per mm square, internal pressure Pi equal to 5 Newton per millimeter square. For the R is the radius at which we have to find the tangential stress. So at this case, R equal to internal radius equal to 100 mm. So substitute this value, R equal to 100 mm Pi 5 Newton per mm square, internal dia equal to 200 mm and outer dia equal to 300 mm. I can get sigma T equal to 13 megapascal. Sigma T equal to 13 megapascal at R equal to 100 mm. Now we can use the same equation. We have to find the sigma T at R equal to mean radius, that is 125 mm. So substituting the same equation, substitute R by 125 mm, I can get the equation. After substitution, I will get sigma T equal to 5 into 200 square. 5 is the internal pressure, 200 is the internal dia, divided by 4 into, instead of R, I will substitute 125 mm, 125 square into 4 into 125 square, that is R square, plus DO square. DO is equal to 300 mm, 300 square divided by 300 square minus inner dia is 200 square. I will get this value, sigma T at R equal to 125 equal to 9.76 Newton per mm square. Further, I can find the same value at the outer radius, substituting R equal to RO equal to 150 mm. I will get sigma T at R equal to 150 mm. Doing the same step with R equal to 150 mm, I will get sigma T equal to 8 Newton per mm square. So this completes our step for finding tangential stress at different radius. Now we can find the radial stress for these equations. My equation for radial stress will be equal to sigma R equal to Pi di square divided by 4R square into 4R square minus DO square divided by DO square minus di square. DO equal to 300 mm, di equal to 200 mm. We can substitute different values of R as 100, 125 and 150 mm, and inner dia equal to 200 mm. 200 mm. Pi equal to 5 Newton per mm square. I will get different values of sigma R. In first case, when R equal to Ri equal to 100 mm, 100 mm, I will get sigma R at R equal to 100 mm equal to minus 5 Newton per mm square. It shows that this stress is compressive in nature. Compressive. Further, I can find the stress at middle region. I will get sigma R at R equal to 125 mm equal to 1.76 Newton per mm square. Further, in the next case, at the outer radius, I will get RO equal to 150 mm. 150 mm. Substituting the value of R, sigma R will be equal to 5 into 200 square divided by 4 into 150 square into multiplied by the value will be equal to 0, will be equal to, you will get that value equal to 0 Newton per mm square. So there is no stress, there is no radius stress at the outer radius. This completes our question. Very simple questions. You just need to substitute the values, do it right, do proper calculation on the calculator, you will get these answers. Now we have the another question. A hydraulic press has a maximum capacity of 1000. This hydraulic press is used for forging presses, screw press, forging press. They are used for forging. So there will be from hydraulic press. I'll draw a schematic diagram. So there is a cylinder in which there will be a piston, and that piston will be moving forward and backward. Here we have the internal pressure, and that piston will be exerting a force F. Here we have the liquid or the fluid at the higher pressure P, which is acting over an area of the piston. So this is a cylinder, there is a piston. Okay, so this is our case. In this, maximum force which it can exert F equal to 1000 kilonewton, 1000 into 10 power 3 Newton. Piston dia equal to 250 mm. Since nothing is mentioned about the piston rod, I can take it as negligible. So the total pressure act on the area of the piston. Calculate the wall thickness. Cylinder is made of material for tensile strength 80 megapascal. Assume material as a brittle material. So material can be considered as either brittle or tensile. If we consider it as a brittle material, we need not consider the Poisson's ratio. Okay, so we have the Lami's equation developed for brittle materials, considering maximum normal stress theory. T equal to di by 2 into sigma t plus pi by sigma t minus pi all under root minus 1. So we have to get this thickness. What is the thickness of the wall? Here internal dia is given 250 mm. Sigma t is the maximum tensile stress. Tensile stress equal to 80 megapascal. Since factor of safety is not given, I am taking that value as such. So sigma t equal to 80 megapascal. Pi is the internal pressure, given internal pressure equal to, which is not given directly. I can find that internal pressure. How will I find the internal pressure? Internal pressure equal to force per area. What is the maximum force it can exert? Force exerted equal to 1000 kilonewton, 1000 into 10 power 3, which is acting on the area of that piston. The diameter is d. My area will be equal to pi by 4 d square. Area will be equal to dia is d. Area will be pi by 4 d square. So pi by 4 into d square, diameter equal to 250 square. So I can get pressure acting on this area. So after calculation, I will get 20.37 Newton per mm square. I can take this value to this equation, 20.37. After substitution, I will get T equal to 37.17. This is our required answer. So whenever we are given capacity, we should know how to find the pressure from this force. So pressure equal to force per area. That's the only thing we have to remember in this question. Rest all the values, all the equations are given in the data book. We just need to substitute those values. Now we can go to the third question. A closed end cast in cylinder of 200 mm inside dia has to carry a fluid at a pressure of 10 Newton per mm square. Permissible stress is 18 megapascal. So sigma T is given as 18 megapascal. Substitute all those values. So inner dia equal to 200 mm. Sigma T equal to 200. Inner dia equal to 200 mm. Di equal to 200 mm given. Then sigma T permissible stress equal to 18 megapascal. I believe it was already divided by factor of safety. And internal pressure equal to 10 Newton per mm square. Determine the wall thickness by means of Lami's and maximum shear stress equation. So we have the Lami's equation from page 103, equation 7.11g. I have this equation. All the values are known. Sigma T is known. Sigma T equal to 18 megapascal, 18 Newton per mm square, and the internal pressure equal to 10 Newton per mm square. Just we have to substitute those values. Sorry. And when you substitute, after substitution, you will get T equal to 100 into root 3.5 minus 1. I am giving this calculation just because you have to check whether you are getting these values. When you get simple equations, there are more chances to make mistakes. Sometimes you will be forgetting to take this root. So you should substitute all these values. You should put your mind when you do such very simple questions, because simple questions are more easy to make mistakes. Okay. So you get 87.08 mm. Now we have to consider maximum shear stress theory. There is something given in addition. What result would you use? Give reason for your conclusion. Okay. So we will put in this second equation maximum shear stress equation. So we will see what happens in the maximum shear stress equation. Here also Di equal to 200 mm, sigma T equal to 18 megapascal, and internal pressure equal to 10 Newton per mm square. There is something special about the denominator. I will get denominator value as such as 18 minus 2 into 10, which becomes a negative value. And we cannot find the negative value. 18 minus 2 into 10 becomes minus 2. I cannot find the root of a negative value. It becomes imaginary. So it becomes impossible to find a thickness for such a value. So our conclusion will be equal to, it is impossible to design a cylinder with given details using maximum shear stress theory. So we can only use maximum normal stress theory, and we can find that value as 87.08 mm. So this is our complete conclusion. Now we can go to the fourth question. A cast steel cylinder 350 mm inside dia has to contain liquid at a pressure of 13.5 Newton per mm square. So inner dia is known. Inner dia Di equal to 350 mm. So 350 mm. Internal pressure equal to 13.5. 13.5, very high pressure. It is closed at both ends by flat cover plates made of alloy steel and are attached by bolts. Determine the wall thickness of the cylinder if the maximum hoop stress on the material is not to exceed, is limited to 55 megapascal. So hoop stress sigma T is given as 55 megapascal. Internal pressure is also given. Find the wall thickness. So since the pressure is at a higher value, we can use the equation for the thick cylinder equations. So wall thickness from page for thick cylinder equation. This is our equation. Di equal to 350 mm, sigma T equal to 55 megapascal, internal pressure equal to 13.5. It is a higher value, so I am using this equation for thick cylinder equation. So T equal to 175 into root 1.65 minus 1. This is a equation after the substitution. I'll get 49.83 mm. So this completes our first step to find the wall thickness. Second one, calculate the minimum thickness of the cover plate. This equation is given in page 405. So you have to use that equation 18.3c. We have similar equation, T equal to D into root of P by 6 sigma T. All the values are known. D is inner dia, that is equal to 350 mm. P is the internal pressure, 13.5 Newton per mm square, and sigma T equal to is the maximum stress it can withstand. For the cover plate, maximum stress should not exceed 65 megapascal. 65. So you will get thickness T equal to 350 into root P by P equal to 13.5. That's the value P divided by 6 into sigma T. Sigma T equal to 65. Sigma T, and this is D. You will get 65.11 mm. Now we have the final problem, which is for shrink fit. When we have compound cylinders where one cylinder is fitted over another cylinder, we have shrink fit problems. So in such questions, we will be having two cylinders, one fitted over the other. So now we can consider this question. A steel tube 240 mm external dia is shrunk on another steel tube of 80 mm internal dia. So we can draw the diagram. So there is a cylinder of dia, outer dia 240 mm, outer dia 240 mm, which is fitted over another one of internal dia 80 mm. So there is another cylinder of dia, internal dia 80 mm, and after shrinking the diameter at the junction, this is the junction, at the junction dia equal to 160 mm, 160 mm. Before shrinking, the difference of the diameters at the junction was 0.08 mm, and if Young's modulus of velocity equal to 200 gigapascal equal to 200 into 10 power 3 Newton per mm square, find the radial stress at the junction. Okay, radial stress at the junction. So we have this equation. This is our equation where B is the allowance, or the what is the shrinkage in the, or difference in diameters at the junction. B denotes the difference in the junction. In this question, B is given as 0.08 mm in diameter, and modulus of velocity is given as 200 into 10 power 3. Thus we have to substitute all those values. Diameter at the contact, DC is the diameter at the contact, or the diameter at the junction, dia at the contact surface. contact surface. In this question, its diameter is given as 160 mm. 160 mm. And outer dia after shrinkage it is 240 mm. 240 mm. And inner dia di will be was given as 80 mm. So I can substitute this value. DC equal to 160 mm, DO equal to 240 mm, DI equal to 80 mm. After substitution in this equation, I will get the radial stress at the junction. Radial stress PC equal to radial stress is same as the pressure between the contact surface. PC is the pressure at the contact surface. Pressure at contact surface equal to radial stress. You will get that value equal to 23.4 Newton per millimeter square. Further, using this value, I can find the tangential stress at the outer surface from page 105. Page 105, equation 7.16b. We have this pressure at the contact surface, that is 23.4 Newton per mm square. DC was equal to 160 mm. Diameter at the contact. Inner dia was equal to 80 mm. Mu is the Poisson ratio. Poisson ratio. It is given the material as steel. It is given more. It is made of steel material. So we should remember what is the Poisson ratio for steel. Poisson ratio can be taken as 0.3. So assume Poisson ratio mu equal to 0.3. I can substitute this value 0.3. And after substitution, I will get sigma T at the outer surface of the inner tube equal to 23.4 minus 23.4 into 1.66 minus 0.3. You will get that value equal to minus 31.98 Newton per mm square. This is the pressure at the outer surface of the inner tube. In addition, we have to find the tangential stress at the inner surface. We have the similar equation. Only thing is that we have to substitute value of DO. DO equal to 240 mm. DC is the contact surface diameter 160 mm. And mu we have assumed as 0.3. And PC equal to 23.4 Newton per mm square. After substitution, I will get sigma T equal to a higher value 67.86 Newton per mm square. Sometimes in some questions it will be given, instead of giving internal diameter as such, we will be giving the volume of the cylinder. So this completes our initial questions. So now we have to see what are the difference which we can find in different question papers. Sometimes the volume will be given, volume of the cylinder, length will be given, and volume will be given. And I can find for cylindrical vessel volume equal to pi by 4 d square area multiplied by length. So if volume is given in some 1 meter cube and length equal to some 0.2 meter, I can find the diameter. What is the diameter? And if we get the diameter, we can substitute on those equations. We can find the all such stresses and thickness of wall thickness or something like that. So you do your problems, study well. And this season where we have a epidemic disease, corona, COVID-19. So you maintain your personal hygiene, and in addition to personal hygiene, you have your vehicles parking in your car porch, take care of that vehicles. And this is a message issued in public interest. Do not engage the handbrake. Keep the tires properly inflated. Start and idle your vehicle. Adjust the wiper blades. And it's better to keep the wiper blades off from the glass. Sometimes if you start your car and unknowingly if the wipers is put on, it will wipe all the dust over the glass and it can make scratches. Then clean the vehicle and make sure that your underbody is coated so it prevents shearing, to prevent rusting. Okay, so this is issued in public interest by Department of Automobile Engineering, SEMS School of Engineering and Technology. This is regarding your car. And regarding when you have your study time, always remember there is nothing such like a right time. Don't wait for the right time because it never comes. There is nothing like a right time. Just go ahead, do your daily lessons and do it now. My success mantra for you is do it now. Thank you for listening. Have a nice day.